We've been hearing about dynamic programming a lot, but what is it actually? So imagine we're given like a problem, which is also called the main problem here. So the problem is finding the shortest path from A to C, and we all know that all paths from A to C must go through an intermediate point B here. So we can divide our main problem into two subproblems. The first one is finding the shortest path from A to B, and the second subproblem is finding the shortest path from B to C. And so the result of the subproblem one is added with the result of subproblem two to produce the result of the main problem, because we all know that the shortest path from A to B, when it is added with the shortest path from B to C, it will so the result will be the shortest path from A to C. And so that's like the core idea of dynamic programming, that is splitting the main problem into many subproblems, and we can tackle those subproblems easily. If we further divide this subproblem into smaller subproblems, which are easier to solve. Um, yeah. There are many types of like dynamic programming approaches. But one of those like concepts is the sequential decision making dynamic programming. So what is sequential decision making DP or dynamic programming? Well, so in short, it's like you have like you start from a smaller subproblem, and you combine that result, the result of the smaller subproblem, with another number, or other numbers, to form the result for a larger subproblem. And from that larger subproblem, you also combine that with another number and stuff to like produce the result for the main problem here. And so one of the like examples of this type of dynamic programming is the house robber. This is a house robber problem, which is also a LeetCode problem, where you can go to LeetCode and search house robber. Essentially, this problem is about. I mean, you can pause the video to have a read on of the problem description, but just I'm gonna just go through this fast. So essentially we are given an array nums representing the money amounts of houses, and we want to maximize the amount of money, like the total amount of money that we can rob from these houses, but with a constraint, that is we cannot rob two adjacent houses. So we can't really rob these two houses. We cannot rob 2 and 3 because those are the adjacent houses. And so let's go through example 2 here. Yep. So, all right. So first of all, we have the subproblem 1. This is the first subproblem. And our subproblem. So our problem is like the main problem is that we want to find like the maximum amount of money that we can rob in all of these houses, right? But we will start from the smallest subproblem, which is subproblem 1. So we're asking ourselves, what is the maximum amount of money that we can rob from the first house? So it's obviously, just the first house, right? Because it's the only house that we can rob up to this point. And so this array is like the original array nums that is given. And this is an array that we use to store the maximum amount of money that we can rob up to each index. So for example, this 2 here, it means that then the maximum amount of money that we can rob up to the first house is 2. And when we come to this, we can store here the maximum amount of money that we can rob up to the second house. That means including the first house and the second house. All right. So yeah, the result of the first subproblem is 2, and we move on to the next subproblem. So the next subproblem is all right. So we've previously computed the maximum amount of money that we can rob up to the first house, and now we're asking ourselves, what is the maximum amount of money that we can rob up to the second house? That means including like from the first house to the second house. So like this yellow highlighted range of the array. And so the results will be stored in this cell. And so we in on this on this here, it's obviously 7 because if we look at the two amounts of money of these two houses, we can see that when we come to this second house, we can decide whether to rob this house or not. Because if we decide to rob this house, then we cannot rob the first house, right? Because it's like it's a constraint. We cannot rob two adjacent houses. But we can also decide not to rob this house, but we can rob the first house. So we have two choices: rob this one and ignore this one, or ignore this one and rob this one. And our solution, the result stored here, will be the maximum it will be the result of whatever decision we made. So which is the max of subproblem 1, which is this, and also number 7. So obviously our choice here is to ignore the first house and rob the second house, right? Because this gives us 7, which is obviously more than the other decision, which only gives us 2 because we ignore the second house. So this is 7. And yes, and up to subproblem 3, now we ask ourselves, what is the maximum amount of money that I can rob from the first house up to the third house? So now we look back and we can see that, okay, so now if I decide to rob this third house, then I cannot rob this second house, but obviously I can rob the first house, right? Because robbing the first and the third house is still a valid solution, which does not violate the constraints. But my second choice is that I can ignore this house and then I can rob whatever I have, like the maximum amount of money that I can rob up to the second house, right? So which choice should we make? Should we rob this house and then rob everything up to the first house, skipping the second house because it's adjacent, or we should skip this house and rob everything we can, no, not everything we can, but like the maximum amount of money we can up to the second house. So it's like 9 plus 2, that is the first decision, robbing this house and this house, so that's 11. But if I ignore this house and I rob like a maximum amount of money up to the second house, then I would get 7. So which one is better? Should I get like 2 plus 9, that is 11, or should I get 7? Well, obviously it's 11, right? So the maximum amount of money up to the third house is 11. And then for subproblem 4, again, we ask ourselves, what is the maximum amount of money that I can get up to the fourth house? So robbing from the first to the fourth house. And from this, again, we have 2 decisions to make. We either rob this house and then we rob everything up to the second house, skipping the third house because it is an adjacent house, so we cannot rob these 2 houses simultaneously. So yeah, so should I decide to rob this house and then everything up to the second house? That gives me 7. So that's like adding 3 to 7 because which gives us 10. Or should I skip this house and rob everything I can up to the previous adjacent house, which gives me 11? Well, obviously 11 is better than 10, right? So we store 11 here, which implies that we skip this house and we will only rob to the third house. And this is the maximum amount of money that we have up to the fourth house, because we decide not to rob this house. Yes, and so finally, this is subproblem 5, or maybe we can call it like the main problem, because because the question is essentially what's the maximum amount of money that I can rob from the first house up to the last house. So that's basically the problem itself. So now again, we decide either to rob this house or ignore this house. So if we rob this house, then we must ignore this house, and then we can rob everything that we can without violating the constraint up to this house, right? So it's like, so if I decide to rob this house, then we will add 1 to the maximum amount of money that I have got up to this house, that is 11, so that's 12. Or I can ignore this house and then just rob everything that I can up to the previous adjacent house, which is 11. So obviously 12 is greater than 11, so we would choose 12. And 12 is also the correct answer for this input. So yeah. Yeah. And so walking through this, you might have noticed that really we're just utilizing the results from the previous subproblems to calculate like the subsequent subproblems. Because looking at this, for example, when at each iteration we utilize like the calculated result for subproblem. Let's say we are standing at the last problem here, so we're looking at subproblem 3 and subproblem 4. So what's the result for subproblem 3? That is 11, it plus 1, and what's the result for subproblem 4? It's 11 right here. So it's just utilizing the computed results from previous subproblems, and which is the idea here. So this problem, like the result of this subproblem is computed utilizing the result from the previous subproblem and some other number, and that some other number is that number 1 here. Yeah. So yeah, so this is the code for the intuition that we've been talking about. So yeah, the first line is that it's just the length of the array. Yeah, so if the array has the length of 1, it means that it only has 1 element, then well, obviously the maximum amount of money we can rob is everything from that only house. So we return like the only house in the array. By the way, this algorithm runs in place, which means that it does not need like an auxiliary array, like what we see here. So what we have seen in this, it looks like that we need a second array besides from the original array given by LeetCode. So yeah, but we actually don't really need the auxiliary array. We can just overwrite the existing values in the original array, because we know that so for at each iteration we only look back at the values computed for the previous subproblems, and so like we don't really look back at the actual values in the original array. That's why we can overwrite those values with the computed subproblems values. So yeah. So nums1, which means at iteration 1 at the second element here, we choose between we choose the greater value between num0 and nums1, which is this and this. It is just because at the second subproblem here, which is essentially deciding whether to include this house or not. So if we include this house, then it should be this and then not this. Or if we decide not to include this house, then it's like not this but include this. So there are two choices, and we obviously go for like the optimal one, so like the maximum between this and this. So either the first house or the second house, we cannot rob two of them simultaneously. So that's why math.max here, and it's stored in nums1 because it represents like the maximum amount of money that we can rob up to the second house by either choosing to rob the second house, which is nums1, or rob only the first house, which is nums0. Yep. And then for I, from this from the third index, from this part and up to the end, we will so for each iteration, for each index from here, from the third index to the last index, we go through an iteration. So for each index we go through an iteration, and what each iteration essentially does is that so for example, if I say at this iteration is I, this iteration is I minus 1, and this iteration is I minus 2, and I'll have this. So we will check. It's just like the same as what we did before. So we look so at iteration I, we look back at iteration I minus 2, which means that, okay, so I have two decisions, right? My first decision is that I will rob this house, which is the house at nums I, and then I will skip the house at I minus 1, but I will rob everything that I could until the house I minus 2, that is 11. So like nums I minus 2 plus nums I, which is this one, nums1 I minus 2 plus nums I. And the second decision is that I will skip this house, which means that I can safely rob the adjacent house, which means the house at nums I minus 1, which is this one. So I will write in here, I will store in here whichever decision leads to the greater amount of money that I can rob. And so until the end, we return nums n minus 1, which is also the last element, because the last one essentially represents the maximum amount of money that I can rob from the first house up to the last house, which is also the main problem itself. And so we can go here and test our code. This is the same code snippet as shown in the slide. So you can click submit to confirm that this solution is correct. Yes, and it is correct. And it also has like a perfect runtime, 0 milliseconds, because it takes like linear time, because if you look at it, if we look at it, we only go through the array only once, and the array has like n elements, so that's O of n time, and the space is O of 1, which is constant because we do not use any auxiliary space. We only overwrite the existing nums array. So yeah, thanks for watching. I hope you guys find this enthralling and interesting and insightful for your studies. Good luck.